All right, so if we've got this function, and all I've done is I've created just a piecewise function here, but it doesn't really matter what type of function you're dealing with. I'm going to take that point right there, okay? So there's an x value, okay? And maybe we'll write it this way. Instead of calling it an x value, let's call it just a, okay? Would this function here be f of a? Make sense? Okay. And let's say at this point over here, at 5 is b. Would that be f of b? All right. So what do they ask us to do then? Okay, and a couple of these net change, average rate of change type of questions is they ask you, looking from A to B in just that interval, just focus your attention on that interval. So again, that is looking, if we highlight the curve in green, we're only interested in, right now, that portion of the curve. Okay? If they want the net change, okay, the net change is taking this f of a value and that f of b value and finding their difference. Does that make sense? Okay. Now, is my net change increasing or decreasing from that picture? It's decreasing, right? So my net change goes from a y value of 1 to a y value of -2, right? So 1 minus -2 is 3, right? But I'm going down, so the net change is -3. Okay? So you see that the net change is simply just how far you have fallen on the y-axis. Okay? From one point to the next. Or maybe if my net change for some reason is increasing from left to right, it'd be a positive number then. Okay? So net change is simply f of b minus f of a. Okay? And it's a good idea to also have that recognition of whether you're increasing or decreasing in regards to that function. Also, so that's like if my net income or something like that. Okay, that's that relationship we made there. But now they want to know what is the average rate of change. Well, the average rate of change is to figure out how fast you are falling per 1 unit on the x-axis. Okay, so they want to know average rate of change is, okay, from here to there we fell 3 units, right? Now they want to know, well, what is that average per unit of x? Okay, so per how far do you fall from -2 to -1? How far do you fall from -1 to 0? How far do you fall from 0 to 1? And that should be constant. Does that make sense? It should be the same number. So what we do is we take f of b minus f of a, and then we divide that by a minus b. And that becomes my average rate of change. Okay? And my hopes are that you realize that that is the same thing. F of b is a second y value. F of a is an initial y value. Okay? I guess I should have this backwards. B's need to be aligned with each other. Because b is an x value, and a is another x value. Okay? And to get the right sign with the average rate of change, we need the subscripts to match up kind of vertically there. Okay, so y2 minus y1 and x2 minus x1. So those two things are syntax. When we see average rate of change, they're simply asking us the slope. Now, what are they asking the slope of? Now, here's where we've got to pay attention. And we mentioned this briefly last week, but if I've got the point, we were at, negative, get this out of the way. -2, 1 was that point there. And then I was at 5, -2, I think. Okay, so those are the 2 points that we found that we were using the slope concept with, the average rate of change. But what we're really doing is finding the slope of that line right there. Okay, and if you've been inside WebAssign, what are they calling that line in WebAssign? Starts with an S. That's your secant line. Okay, if you remember back to geometry, if we had Well, that's not what I wanted. Plus y minus 4 squared equals 16. Okay, got a circle, right? Back in geometry, whenever we had something like that, okay, this line that intersects your curve 2 times, we called that a secant for the circle, okay? Now, this segment, let's see, intersect. What do we call the segment from C to D? Anybody remember that? Not diameter. A diameter is a type of one. It's the diameter here because maybe that's the diameter. Does that make sense? But that one, maybe not. It's a chord. Okay. So by definition, simply a secant is a line that contains a chord. Does that make sense? Okay. And if we go back to this idea here, you extend that line beyond what I have as dotted. It's a continuous line, right? It goes on forever. So we call it a secant line. But if you go back to the idea of kind of cutting it off, maybe you consider it a chord. But we call it in calculus, we call that a secant. And we can move that anywhere we want, okay, as long as it's intersecting both curves. So here, when I ask it to find the slope, there we go, of that line there, we get negative 0.43, okay? And that's because we're taking, well, we had a drop as 3, right? Okay, so there's our change in y, but our change in x is now 7, right? Okay, well, 3 divided by 7 is 0.43, and it's decreasing, okay? So it's negative 3 divided by 7, and that gives me that slope there. Okay, but that's all they're asking for you when you're being asked what net change is and what average rate of change is. They're directly linked to one another. Net change is simply just the numerator of your slope function, and then average rate of change is divided by how many x values you have been passing through. Does that kind of make sense? And like I said, that dotted line they refer to as the secant line. So make sure that you understand that terminology. Adam?
So is the average rate of change between the two functions, is that equal to the slope of theta?
Don't worry about the fact that there's two functions here. Let's because it's just one function. Now it's piecewise, but collectively it should just be one curve. Does that kind of make sense? But the average rate of change is in this situation, maybe it's not extremely indicative of the slope of the function at those points. Does that kind of make sense? Because it's not anywhere in between. So if I'm looking at where my cursor is right now, okay, does negative 0.43 represent that slope very well? No. Okay, and negative 4.3, it might actually represent this slope a little bit better, but it's still not a great representation of that slope, right? But collectively, my rate of change, think of it as kind of like a salary idea or an hourly rate kind of idea. In this case, it'd be decreasing from these two x values. What we do, Adam, is eventually, maybe we want to know the slope of this parabola at negative 2. Okay, so the concept is we now take these points, okay, and we make sure that those points are on the curve. So let me see if I have the tool to attach these. All right, so I attach that point to that curve, and I can move it anywhere I want to on that curve. Does that make sense? Okay. Right now, if I were to find the slope between those 2 points, which is saying it's 2.27, does it look like that secant line is right on top of that curve? Almost, right? So that would be a good approximation. 2.27 would be a good approximation for the slope of that curve around an x value of negative 2, negative 1.8, that kind of idea. Does that make sense? Calculus, what calculus does, because we can do this. We can zoom in on this, and when we recognize that the further we zoom in, that secant line is a more and more there's more and more gaps between the secant line and the actual curve, right? So it's really not that great of an approximation. So calculus-wise, what we do, we use a tool called limits to do this, but we bring this point as close to the other point as we can, all right? And now when I zoom in on that, because between those 2 points, I can still find slope, right? And now we're seeing, zoom out, it's saying the slope is 2.01 at that point, okay? But I'm going to zoom in. That's going to take a lot more zooming, but you'll eventually start to see a gap between those two things, right? Okay, so we zoom back out, and what can we do with those 2 points still? And I can put them closer together. So put them there. Zoom in, and I can keep getting them closer. Oh, I don't want that to happen. I can keep getting them closer and closer to one another. Okay, and the more I zoom in and the closer and closer I get them to one another, okay, the more and more accurate that slope is between those 2 points. The more and more accurate the slope is using simply y2 minus y1 over x2 minus x1, but it gives me a great idea that the slope of that curve, okay, at the point of -2 is actually 2. But we use limits to do that, and the idea is that we let the distance between those two, basically x value between those 2 points, approach 0. And when it approaches 0, the distance is going to, the denominator becomes like 0.000000000. It means zeros you can say, and then put a 1 on the end of it. So we're not divided by 0 anymore, right? Does that make sense? But we essentially have then the difference in the y value is divided by a very, very, very small number. And that will give us the slope at that point on the curve. And that's called instantaneous slope, okay? Because at that instant, when x is -2, we have the slope of the curve, okay? But that slope changes throughout the entire curve, right? When my points are here at x of -1, my slope is a lot steeper than 2, right? So throughout that curve, for a line, slope is constant, right? No matter where I'm at on the line, slope is the same. But for curves, slope is always changing, okay? So we call it instantaneous change, because every instant, even if I just move that point of -2 to -2.1, the slope is going to be a little bit steeper at that point. And we go through that entire process again to find the actual slope of the curve. We use something called derivatives to do that with, okay? Because that concept, that procedure graphically takes time, and Isaac Newton, and a guy named Leibniz both came up with derivatives that allow us to find slope much quicker. Okay? So that's kind of what the first 16, 18 weeks of Calc 1 is all about, is finding those derivatives and analyzing the slope or the average rate of change for a function at particular points. Throughout that assignment, they start throwing in and they are kind of vague in what they do. They provide you like a function. They say like f of x is equal to x squared plus 3, and then they say x equals 4 and x equals -4. Okay. Well, what they want you to do is they want you to take in a value of 4, plug that in. Okay, so for 4, plug that in, I get 19 back, right? Okay, and then we'll take -4, plug that in, and I get 19 back, right? Okay, well here's your, if we're using the A and the B kind of terminology again, there's your A and B, there's your f of A and f of B. If you're a person who wants to use x and y, or x and f of x, that's fine, doesn't really matter. But now can we take your y's and subtract them, take your x's and subtract them, and find the average rate of change of it? Okay. And as long as you maintain, because we've talked about how we want, when we talk about net change or something like that, we want to make sure whether it's increasing or decreasing. Well, when they ask me average rate of change for this, as long as the problem, the function doesn't know which one of these I'm letting be A and f of A and B and f of B, So as long as I got the like f of b minus f of a, and then if that was b, then that's got to be b, and that was a, that's got to be a. As long as I got them in the correct order, okay, the sign will work out by itself, plus or minus. Okay. Now if I mess the order up, if I go f of a minus f of b, and on the bottom I keep it b minus a, I have the opposite answer. Okay, so if the answer ends up being like 3, I'd have negative 3 showing up. So just be careful of that. That's all they're asking you to do there. I think they do a poor job. They should write maybe if those are 2 different x values, x1 and x2. I think that provides some confusion for people. Does that help? Is there anything that you guys want to talk about specifically throughout either of those assignments? 2.5 average rate of change or 2.6, which is you're both due tomorrow, correct? Yeah. If I plug negative 4 and I square it, I get 16, right? And then add 3 to it, I get 19. No questions? 2.6?
Okay, do you want to make number 23?
23.